Alright, so we'll start with alkenes and alkynes. These are unsaturated hydrocarbons. The unsaturated hydrocarbons basically consist of at least a double or a triple bond, at least one double or triple bond between two carbon atoms. There are two types. The ones that contain a double bond are called alkenes, and the one that contain a triple bond are called alkynes. Okay, so the general formula for this alkene is basically CnH2n, and general formula for alkyne is CnH2n minus 2. So if you remember, alkanes was CnH2n plus 2, right? Alkanes have all single bonds. Alkenes have at least one double bond, therefore they have two less hydrogen. So you can basically get rid of this. Every double bond, every bond that we increase gets rid of two hydrogens. So this would be CnH2n. Alkynes, we add one more bond, so it becomes a triple bond. So the formula would lose another two hydrogens. So it would be CnH2n minus 2. Bless you. Okay, now we go to aromatic hydrocarbons. The last thing that we'll see today would be a third kind, which is aromatic hydrocarbons, which would consist of, either they consist of 3 double bonds that are alternating with 3 single bonds in a 6 carbon ring. So essentially, what does it consist of? You can see right here, it has this 6-membered ring, carbon, 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 6 carbons, and you see alternating double bonds. So there's a double bond right here, single bond, double bond, single bond, double bond, single bond. So these double bond and single bonds are alternating. If we were to draw the line structure of this, it would look like this. It's a 6-membered ring, and then we have alternating double and single bond. So double bond, single bond, double bond, single bond, double bond. Okay, so this is how an aromatic compound looks like. This ring is called benzene. Okay, so whenever a structure consists of benzene, it is called an aromatic compound. Why aromatic? Because most of these compounds usually have some aroma to them. They have an odor, so therefore they are called aromatic compounds or aromatic hydrocarbons. Okay, we'll talk more about these aromatic compounds later on, but let's first continue with alkenes and alkynes. They are called unsaturated because alkenes and alkynes, because they do not contain the maximum number of hydrogen atoms. Okay, if we want to add more hydrogen atom, we could simply do a reaction of alkenes or alkynes with hydrogen gas and add some hydrogen atoms into this to form alkenes. So therefore they are called unsaturated. They don't have enough hydrogen atoms in them, but every carbon still will be making 4 bonds. Okay, every carbon here still 4 bonds. So what would be the smallest alkene or simplest alkene that is possible? We need a double bond between the carbon atoms. So in order to have double bond, the smallest means we have to have at least 2 carbons, right? We cannot simply make a double bond with 1 carbon atom. So you need at least 2 carbon atoms. What would be the formula for a 2 carbon alkene? It is CnH2n. So that would be C2H4. So how would you draw it? You draw 2 carbons and they consist of a double bond between them, and then we add hydrogens. We distribute the hydrogens evenly to both the carbons, and that would make this C2H4. Another thing you can confirm here is that each of these carbons, you should see that they have 4 bonds at least. So this carbon has 1, 2, 3, 4. So these are 4 bonds in total. This carbon has 1, 2, 3, 4. 4 bonds in total. Yeah. And how do you name these alkenes? You see, the name is called alkene. So the ending is basically happening with ene. So you're going to use the same prefixes that we saw for alkenes. the prefix of the number of carbon atoms followed by E and E, and that would give you the name of the alkene. Okay, as long as, for instance, in this case, this, what would this be called? This is 2 carbons, so 2 carbon prefixes eth, so this will be called ethene. Okay, now in this case it's easy because there is only one possibility where we can have a double bond. Sometimes if you have a very long hydrocarbon and the double bond is, let's say, in the middle, you do have to tell where the double bond is located. So you do have to mention sometimes where exactly the double bond is. Okay, we'll come to those examples in a bit. Let's look at alkynes. So if we talk about, again, alkynes have at least one or more carbon-carbon triple bond. So if I talk about the smallest alkyne possible, that would again be 2 carbons. What's the formula? General is CnH2n-2. So if it is 2 carbons, that would be C2. H would be 2 times 2 would give you 4. 4 minus 2 would give you 2. So C2H2. How would you draw this? Carbon, carbon, single bond, but you see here you would distribute the hydrogens evenly. So I distribute 1 hydrogen to this, 1 hydrogen to this. The carbon needs how many bonds in total? 4 in total, right? So this is 1, 2, it already has 2 bonds, so it needs 2 more, but there are no more hydrogens, so you would draw a triple bond between carbons. Same thing here. Now this has 1, 2, 3, 4 bonds in total. So that would be the structure of alkyne. And how do you name them? Same approach. You use the prefix for the number of carbon atoms followed by Y and E. That would be the name of the alkyne. So in this case it is 2 carbons, so it would be again eth, and because it's a triple bond it would be ethyne, Y and E, right? You could do ethyne, propyne, butane. That essentially means it's 3 carbon with 1 triple bond. Butane would be 4 carbons with 1 triple bond. Okay, here you don't have to tell me that the triple bond is between carbon 1 and carbon 2 because there's only 2 carbons possible in ethyne, right? So for instance, the simplest question could be identify the following compounds as alkene or alkyne. So A is alkene because it has a double bond, and B is alkyne because it has, this is the triple bond. Okay, perfect. So one thing that you would see here, the triple bond is always drawn in straight line. Okay, because whenever we draw a triple bond, that would make the molecule in a linear format. The bond angle is going to be 180 degrees. So you cannot draw a triple bond like this. You cannot simply say that, okay, this is my hydrocarbon. If you were drawing a line structure, let's say you were doing this, you cannot simply draw a triple bond right here. It has to be, if this was the structure, it would be something like this. This triple bond is in the middle and then it goes the other way and you can follow along. Alright. Okay, next we'll talk about naming. Like we saw, you simply name, their names are very similar to alkane. You use the name of the alkane with the same number of carbon atoms and replace ane with ene or ane with ine, depending on we have alkane, alkene or alkyne. Okay, so for instance, see here, if we are drawing propene, that would be 3 carbons, 1, 2, 3 with 1 double bond. Okay, so you could draw it as a curved structure. But if you were drawing alkyne, it is drawn as like this. Okay, so this, when you see, is still 3 carbons. How? This is carbon 1, this is carbon 2, this is carbon 3. You would not see this as a zigzag line because alkynes would always form like a 180 degree bond angle. Okay, so what would this be? Essentially that means if you see wherever these smaller bonds end, that is one of the carbons. Okay, so this is a 3 carbon compound. Okay, now let's see how would you name the structure, same thing. Name the alkane, whatever the name of the alkane is, and then simply replace the ane with ene or ine. Okay, so for instance, if this has a double bond, so we know this is alkene, right? How do you start naming it? Now you have to tell me where the double bond is located. Okay, so we need to find our longest chain here. Longest chain would be, we can see it is 1, 2, 3, 4, 5, or it could be 1, 2, 3, 4, 5. It really doesn't matter. You could go up or you could go down. It's eventually giving you total number of carbon as 5. But now the question is, should I start numbering from left or should I start numbering from the right side? You will give preference to the double bond or the triple bond. So the double bond or the triple bond should get the smallest number possible. Okay, so in this case we have a double bond and we have a substituent as well. So here the double bond should get the smallest number. So if you start from here, 1, 2, 3, 4, 5. This is my long chain. And this is a substituent and there is a double bond in between. Okay. Now where is the double bond located? The double bond is between carbon number 2 and carbon number 3. So when you write where is the double bond, you will give the smaller number, which is in smaller carbon number, which is involved in the double bond. Okay. So if you tell me this is the double bond is at carbon number 2, I would know that it is between carbon 2 and carbon 3. Okay, so how would we name this? If it was alkane, forget about the double bond. If it was alkane, it would be a pentane, right? So if it was alkane, it would be pentane. Since this is alkene, we are going to replace the ane with ene. Where is the double bond located? The double bond is at carbon number 2. It is between carbon 2 and 3. Whichever is the smaller number, we usually write that. And now we name the substituent.
So if the double bond is between 1 and 2, I would say 1.
You would say 1, or you would simply not put a number. 1, we usually don't write the number. It essentially means it would be at carbon number 1 if no number is given. Okay, but since this is at carbon 2, you do have to mention this is at carbon 2. So it would be 2-pentene is the parent chain. Now we come to substituent. Our substituent is again, how many carbons is this? This is only 1 carbon because I only see 1 corner. The second corner is already counted in the long chain. So 1 carbon means this is methyl. And where is it located? It's located on carbon 4. So this will be 4-methyl-2-pentene. Sometimes people also write it as 4-methyl pent-2-ene, which is also okay. This is also acceptable. If your double bond is between carbon 1 and 2, you essentially don't have to mention the number 1, because if you simply write pentene, one would assume that you are telling that this is a 5 carbon compound, so you would draw 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 carbons, and you're telling me this is pentene, so I would just simply assume, since you haven't given me a number where the double bond is, I would draw it between carbon 1 and carbon 2. So therefore, if it is not carbon number 1, it is crucial that you tell exactly which carbon is involved in the double bond. Now let's name the second structure. So first thing, when you look at the structure, you see a triple bond. That means this is alkyne. So now how do we name alkynes? Same approach. You name the alkene first and then replace the ane with ine. So if there was no triple bond, I would name this as carbon 1, 2, 3, 4, 5, 6. This is 6 carbons. Okay. And again, since you see a triple bond, the triple bond will be given the preference. So our numbering will start so that the triple bond gets the smallest number possible. So we go from right to left. And remember this, wherever these smaller bonds end, that is where you have a carbon. So if this is 1, this would be 2, 3, 4, 5, 6. So this is hex, 6 carbon, so it is hex. It is alkyne, so this is hexyne. Where exactly is the double bond? The double bond is triple bond is between carbon 2 and 3. So this is going to be 2-hexyne. The important thing here to remember is that whenever you draw a triple bond, you keep it as a straight line. Okay, so let's say if we were to draw the structure of 3-pentyne, what would be the structure? So we draw carbons as carbon 1, 2. If the triple bond is between carbon 3 and 4, that means it has to be a straight line. 5. Oops. So this is 1. Oh. This is 1, this is 2. Somewhere at between carbon 3 and 4 is my triple bond. So this is 3, this is 4. And then I have a corner which is 5. So let me draw this like a straight line so it doesn't look like there is another carbon in between. So this would be 5. So you need to make sure that this stays as a straight line. Okay, so let's see, how would you name this? So what we have here is, I see this is a straight chain and it has a double bond. So we need to give preference to the double bond. So I need to start numbering my carbons to know how many carbons it is. I could start from left or I could start from right because there are only 2 corners here. If I start from the right corner, my double bond will get a much bigger number. Therefore, I'm going to start from the left corner so that the double bond gets the smallest number possible. So this would give us a total number of carbons as 8. 8 carbon means it is oct, and since this is alkene, this will be octene. And where is the double bond located? Between 3 and 4, so this would be 3-octene. Okay, let's try one more structure. Let's see this. How would we name this particular structure? We see that this is a alkyne. It has a triple bond, right? So how do I name alkynes? Same approach. I first find my longest chain and I see if there are any substituents. So I need to name it like an alkane first. So where do I start numbering? I know that this has a triple bond, so my triple bond has to get the smallest number possible. So I will be starting from this corner, that is, I'm sure. I go 1, this is 2, 3, 4, 5, 6, 7. That gives me total of 7 carbons. I do have another option where I can go straight instead of coming down. So I could do 1, 2, 3, 4, 5, 6, 7, 8. So if I do this, then I am getting a longer chain which is 8 carbons. So I'm going to stick with the 8 carbons. I'll get rid of the other chain because that's not my longest chain. So now this is my longest chain. So if this is the longest chain, I do have a substituent as well. I have a substituent which is right here. So we need to name our substituent and our longest chain. What would be the name of our parent chain? It is 8 carbons, so it is oct, and it has a triple bond, so it is YNE. Where is the triple bond? The triple bond is on carbon number 1. So we really don't have to tell that this is 1 octyne. We could, but technically whenever it's on carbon 1, we usually don't use this number, so I'm going to get rid of this number. Now we have to give the name of the substituent. The substituent is right here. How many carbons is the substituent? 1, 2, 3. Perfect. Again, you do not count this carbon because this carbon is already part of the long chain or parent chain. So 3 carbon is propyl. As long as the chain is a substituent, the carbon chain is a substituent, the name would be alkyl. It's called an alkyl group now. It's no longer propane. Okay. So where is it located? This is on carbon 4. So this would be 4 propyl or 4 propyl octyne. Please replace this alkyl group with a Cl or Br. The naming stays the same. It would be chloro, bromo, whatever needed. Just how we name the alkane, we name it similar to that. Only difference is ane is replaced by ine. So those are the naming of alkenes and alkynes. Next, we also have some cycloalkenes. Cycloalkenes means there would be a double bond and it would be a cyclic structure. Okay, they have a double bond within a ring structure. And how are they named? They are named very similar like we were naming previously. They are named by assigning the double bond to be between carbon 1 and carbon 2 whenever there is a substituent on the ring. Okay, so always the preference, because it's a ring structure, we need to figure out it doesn't have any corners, right? So where do we start numbering? Always the double bond is given the preference, and double bond is assumed that it is between carbon 1 and carbon number 2. So you really never tell where the double bond is located because it's assumed that it is always at carbon number 1. Okay, so if we were to name this compound, how would we name this? We see that it has CH3, which is the methyl group, which is our substituent. And we know that it has a double bond. So this is a cyclic structure and this is alkene. So this is a cycloalkene. And what is the rule? This double bond always gets carbon number 1. So I'll do carbon 1, 2, 3, 4, 5. Okay. Why did we go counterclockwise? Why did I go up and why did I not go down? Because if I go down, this would be 1, this would be 2. Let's write those numbers as well. This would be 1, this would be 2, but my double bond should be between carbon 1 and 2. So the double bond is right here. So this would be 1, 2. Okay. Other thing someone can ask, why did I name this one and not this one? If I name this one, this would be 2, which is okay. Double bond is between carbon 1 and 2. But yes, but the substituent then will get a very high number. If I go down, this is 1, 2, 3, 4, 5. My substituent will get carbon number 5. And right now, if I'm doing the numbering this way in the blue fashion, I'm getting the substituent at carbon number 3. So that makes a huge difference. Okay, we want to have the smallest number possible for the substituent as well. That rule still applies. So this would be our numbering. Now what is this structure called? This is a cyclopent. If it was alkane, it would be cyclopentane. This has a double bond, so this will be cyclopentene. That is my parent chain. And again, we don't have to tell that it is carbon 1, which has the double bond. Next, we name the substituent. The substituent is 1 carbon, so it is methyl. Where is it located? On 3rd carbon of the parent chain, so it is 3-methyl cyclopentene. So for instance, let's say if I were to draw this structure, How would we name it? This would simply be one. This is 4 carbon, so this is bute, and it is a cyclic structure, so this is cyclobute. And what would be the name? Cyclobutene. We don't have to say that this is carbon 1 because it's assumed that this would be always between carbon 1 and 2. Okay, now this was cyclobutene. What if I put a Cl right here? How would we name this? Now the numbering would I go numbering counterclockwise or clockwise? Clockwise, right? Because we want to have this would be carbon 1, this would be carbon 2, so that our substituent, the next substituent, can get a smaller number. So this would be 3 and 4. If we go, it's a 4 carbon, so it really doesn't matter. You could go here 1, 2, 3, 4. If you do this, your substituent is getting number 4, which is not the smallest number possible. So therefore we will number it in the clockwise fashion. Okay, so now what would be the name of this compound? This is still cyclobutene, but now this is 3-chlorocyclobutene. So let's see if we can name these alkenes and alkynes. In the first one, if we see this is a cyclic structure and it has a double bond, which means this is a cycloalkene. How many carbons? We can do carbon 1. Double bond is always between 1 and 2. There are no substituents, so you could go counterclockwise, clockwise, does not matter. 3, 4, 5, 6. It's a 6-membered ring, so name would be cyclohexene. We don't have to tell the number where the double bond is. Next we go to the next structure, which is, again I see a cycloalkene, but this has substituents. So I need to know how should I number it. If I go in this direction, if I start numbering from here, if I make this one and I go in this particular direction, my substituent will get a very big number, right? Whereas if I start from this side and I start numbering, I make this as 1 and I start numbering in this direction, my substituent will get a smaller number. So basically you don't always have to number it, you could just simply by working with the structure, you could figure that out. Okay, so more you practice, you would figure out how to put the numbers. So I'll start from this direction, 1, 2, 3, 4, 5, and that's it. 5 carbons. The double bond is between 1 and 2, and I have substituents, which I have 2 substituents right here, and both are, yes, so this would be, first we name the parent chain. Our parent chain is pent, and it is a cyclic structure, so this is cyclopentene. And now we name our substituents, which is on 3rd carbon, so this would be 3,3-dimethylcyclopentene. We could also draw a structure like this. How would we name this? So if we were to draw this, name this particular compound, again we could start numbering from here. That would be 1, 2, 3, 4, 5. So my substituents are getting 4 and 5. But if I number them the other way, I go 1, 2, 3, 4, 5. If I do this, my substituents are getting a number of smaller number. They're getting 2 and 3. Is that okay though? Can I start numbering from here?
No.
Because have to have the double bond. So that is one very common error that people make you, in order, they just focus on giving the substituent the smaller number. They forget that the double bond has to be between carbon 1 and 2. So if you start from here, 1, 2, 3, 4 and 5, that would be the best numbering that is possible for this particular compound. So I can simply get rid of the ones that I had before. This is the best numbering that I'm getting for this particular structure. So my double bond is between 1 and 2, which is fine, and my substituents are getting the smallest number possible. So now when we name this, it is going to be, again, the parent chain is 1, 2, 3, 4, 5 carbons. Let me write this for a little above, closer, so it doesn't, you don't confuse it with the substituent number. This is 2 and this is 1. So now I have 2 substituents right here and my parent chain. The parent chain is going to be again cyclopentene, and the double bond is between 1 and 2, which is good. Then we name our substituents, which is methyl. This is also methyl. This is also methyl. This is located on 4th carbon. This is located on 3rd carbon. But both are methyl, so I'm going to write it as 3,4 dimethyl cyclopentene. The important thing is, even if there are the methyl groups are present, like in the structure above, they were present on the same carbon, you do have to give the numbers for each of the methyl groups. So as long as there is a substituent, every substituent should follow with a number. Every substituent should have a carbon location associated with it. So those are So the next thing we'll come to is geometric isomerism. Alkenes usually form isomers which are called geometric isomers. Those isomers are called cis and trans isomers. If you remember from the last lecture, we talked about isomers. Isomers have the same molecular formula but a different arrangement of atoms. Okay, so alkenes can form cis-trans isomers. How do they do that? So for instance, if this is my alkene, what does this consist of? It has 2 carbons. There is a double bond between these carbons. Each carbon has 1 hydrogen atom and it has 1 chloride atom or chlorine atom. Right? So each carbon has 1 hydrogen and 1 chlorine. There are 2 ways I can write this structure. It could be the straight double bond in the middle. So this bond doesn't rotate. Okay, this is a straight bond. This is very rigid. It doesn't rotate. What happens? You could have this carbon where the hydrogen is located and the Cl are located in this fashion. And the other one also has hydrogen and Cl like this. We could also, these chlorine and hydrogens can rotate in a clockwise or a counterclockwise fashion so that you have the double bonded carbon which stays the same, and this Cl is same, this hydrogen is same like this carbon, but the hydrogen and chlorine here have rotated. So this hydrogen is now up and this chlorine is now at the bottom. What difference does this make? So in this case you can see that the 2 chlorines on both the carbons are present on the same side of the double bond, and 2 hydrogens are present on the same side of the double bond. Whereas in this particular structure, the chlorine and hydrogen are, the 2 chlorines are present on the opposite sides of the double bond. One is up, one is down. One hydrogen is up, one hydrogen is down. When this group, which is common to both the carbons in a double bond, if they are present on the same side, it is called a cis isomer. If they are present on the opposite sides, it is called the trans isomer. So definition again. So geometric isomers are possible because there is no free rotation at the carbon-carbon double bond, meaning these carbon-carbon double bonds, they do not freely rotate, they are very rigid. So they form cis and trans isomers. Cis isomers will have two similar or identical groups on the same side of the double bond. And trans isomers will have two similar or identical groups on the opposite side of the double bond. So you can see right here, the easiest way to look at this is you look at the structure of the compound and you find which are the common groups that are present on both the carbons. So this has a hydrogen, this also has a hydrogen, they both are on same sides. This has a methyl, this has a methyl group, both are on the same side. If they are on same side, it is cis structure. If they are on opposite side, for instance right here, this also has a hydrogen, this also has a hydrogen, but they are on opposite sides. So this is trans structure. This also has a methyl, this carbon also has a methyl, but they are on opposite sides. Okay, so this is trans 2-butene. Now you will ask, why is this butene? We are only talking about these carbons. Why is it not methyl ethene? Why is that? Because we look for the longest chain possible, right? Straight chain, which is longest. So if we start numbering from here, I would say this is 1, 2, 3, 4. It's a straight chain, right? So that is why sometimes the structures might look weird, but it is still in a straight chain. So you have to make sure that you are drawing the structure. So if I draw this as a line structure, it would be this, this, this. That is a straight chain. But if you see it in line structure, it's easier. Whereas if you see it like this in a condensed form, it becomes a little bit tricky. Okay, so this is 4 carbons with alkene group, or the double bond present between carbon 2 and 3. So therefore this is 2-butene. And it is trans because these groups are present at the double bond. These groups are present on the opposite sides. Okay, this makes a big difference because their properties, their physical properties changes. Whenever the cis and trans isomers are present, they both have different physical properties. Therefore these cis and trans are very important. So you could also remember this, like if you have your 2 hands in front of each other and you look at your thumbs, if both the thumbs are facing same direction, that means this is cis. Whereas if you turn one of the hands, or if you rotate one of the hands, what would happen? This thumb, the 2 thumbs are going to be on the opposite side, which means this is a trans isomer. Okay, so that's exactly how a double bond behaves. If both the groups that are, they have to have a common group though. If there is no common groups, they don't do cis or trans. It has to be a common group on both the carbons that are involved in a double bond. A couple more example, for instance like this. If you're given these 2 structures and you're to identify which one is cis, which one is trans, how would we do that? We know this is the double bonded carbon. Both the bromines, bromine is a common group on both the carbons. Bromines are present on the same side of the double bond. So this is cis. Here the bromine is present on the, one is present on this side, the second is present on the other side of a double bond. So this is your double bond. They are present on opposite sides of the double bond. So this is a trans structure. Okay, let's try this question then. Can you give them a prefix, cis or trans? If we start with number A, look for the common groups. This carbon also has a chlorine. This carbon also has a chlorine. It just needs one common group. It is not necessary it should have both the groups should be common. So this would be, they both are on the same side. Yes. So this is going to be cis. Perfect. Moving on to the next one. The common groups that we see are, this also has a Br, this also has a Br, but they are on opposite sides. So this is trans. You could pick bromine or you could pick methyl. Like the methyl here, both of them have a methyl group, but they are on opposite sides. So this is trans. Moving on to the next one, both of them have a methyl group, but they are on opposite sides. So this is also trans. Let's see, if we were to name this compound, what would be the name of this particular alkene? A. We know it is cis, but what would be the name of this compound? How would we start numbering our carbons? We need to find our longest chain. Where is our longest chain? Carbon 1, 2, 3, 4. So these are the 4 carbon alkene again, which is the parent chain will now be called butene. Is the double bond between carbon 1 and 2? No. The double bond is 2 and 3, so you do have to tell that this is 2-butene. And you only put the smaller carbon which is in the double bond. Then it has 2 substituents. It has chloro on carbon 2 and 3. So this will be 2, 3 dash dichloro dash 2-butene. And this is cis, so you would put a cis in front of this. So this would be eventually cis 2,3-dichloro-2-butene. If we were to name the bottom one, how would we name this? The last one, C. This is again, you can see this is straight chain with 4 carbons. So I start from wherever I want, 1, 2, 3, 4, whichever corner. I could start from this corner or that corner, it really doesn't matter. This is again butene. Which type of butene? 2-butene. And do I have any other substituents here? No other substituent. So basically the name would be simply trans 2-butene. And you could only give me a name with cis or trans if the structure is like this, if it's a completely expanded structure at least a double bond. So if the question is giving you in options, that if the question is asking you tell this is cis or trans, only then you need to mention cis or trans in the name. Otherwise you can simply forget about the cis and trans and simply name what the compounds like we have been naming before. Two different types of reactions that these alkenes and alkynes do. One very common reaction that alkenes and alkynes undergo are called addition reaction. Okay, name suggests these reactions are addition of compounds or atoms to the double or the triple bond. So alkenes are very highly reactive. They are chemically very reactive, so they like to react with other compounds. They undergo addition reaction where compound adds atoms to its double bond, okay, and forms new bonds. For instance, if this is the alkene, what does this have? This has a double bond. If I add, let's say, a compound AB to this, what would happen? This double bond will break up. One of these bonds will break. Let's say this bond was lost. This bond was lost. What would happen? Now this carbon and this carbon will have one extra bond available. As we break one bond on each carbon becomes available, and you simply add A to one and B to the other of these bonds, and your final compound will be this. So whenever there is an alkene present, the double bond opens up and you could simply add atoms, that whatever the other reactive atom is, you would add that to that double bonded carbons. The different types of these addition reaction that these undergo are halogenation. Halogenation means we are adding halogens. Again, halogens is group number 7. Next reaction could be hydrogenation. Hydrogenation means we are adding hydrogen. Okay, so we are simply adding hydrogen gas into it. Last one is hydration. Hydration is what? You're adding water. Okay, so names basically tell you what exact addition is happening in each of these reactions. Let's look at one reaction, each reaction at a time. So halogenation means we are adding halogens. Okay, halogens are chlorine, bromine, iodine, fluorine, all of those. Okay, so generally what would happen if we have a compound like this which has a double bond? It could be anywhere. It could be 5 carbon, 6 carbon, 10 carbon, doesn't matter. As long as there is one double bond and we react it with a halogen, this double bond will open up, become a single bond, and you would add one Br to one of the carbon, second Br to the second carbon. Okay, How would the question look like? The question would be simply like this: can you tell what would be the reaction of 1-butene with bromine?
Doesn't matter if the butane is on the top or bottom.
So it really doesn't matter if you draw bromine, one bromine here, one bromine on the other side, it's the same compound, because this cis and trans are only possible in alkenes. There has to be a double bond for cis and trans isomers. They don't exist when it's an alkane. This now is an example of an alkane. So alkenes will turn into alkanes. Okay, for instance, if we have this particular reaction, what would happen? And I ask you, okay, this is the reaction given to you. Can you tell what the products would be? You should know that if there is a double bond, this is an example of addition reaction. What would happen here? One of these double bonds will break. This carbon will have one extra bond. This carbon will now have one extra bond to be made. And you simply add Br to each of these, and your final answer would become an example of an alkane, which has halogens to it. Therefore, these alkanes are called as haloalkanes or alkyl halides. As long as they have a halogen and they're alkanes, they could be called either of these names. Okay, moving on, we'll next reaction, which is hydrogenation. What happens in hydrogenation? We are adding hydrogen. Okay, so the reaction is same. Here you have a double bonded carbon. We simply are going to add hydrogen here. How would this reaction work? Again, one of these bonds is going to break. We'll have one extra bond available on each of these carbons, where we are going to add a hydrogen molecule. Okay. Now, important thing is, whenever hydrogen, you can't simply just add hydrogen to any alkene by itself. You need a catalyst to speed up this reaction. So the catalysts that are involved could be any metallic catalyst like platinum, nickel, or palladium. Okay. As long as you see something like this, this is an example of hydrogenation, where the double bonds will basically turn into a single bond, and an alkene will turn into alkane. This reaction is very commonly actually performed. This addition reaction is done very commonly in industries that prepare oils. So the oils that we consume, like vegetable oil, sunflower oil, canola oil, all the oils that are liquid, they have a double bond in them. They are unsaturated fats. They always have a double bond in them. What do these companies do? You simply pass hydrogen, controlled amount of hydrogen through these oils, and this double bond is converted into a single bond, and the fats are converted from unsaturated fats to saturated fats. And these saturated fats are the examples that we have, like butter or shortening or margarine. All those things are example of saturated fats. Like if you guys have heard before, saturated fats, they say, are not healthy, they are not good for us. Unsaturated fats are better to consume, okay, because they turn into solids even at room temperature. Whereas the unsaturated fats like olive oil, canola oil, vegetable oil, sunflower oil, all those oils are liquid at room temperature. So this is like an example showing you that how hydrogenation reaction is actually used commercially. Okay, for instance, the question is this: write an equation for hydrogenation of 1-butene using a platinum catalyst. So in this case, what are we going to do? We are doing hydrogenation of 1-butene. So first thing we need is a structure of our reactant. Butene means it is 4 carbons. Perfect. So I draw 1, 2, 3, 4. 4 carbons. Where is the double bond located? It's on carbon 1, between 1 and 2. If it was not given, I would simply draw it between 1 and 2 as well. So this is 1 and 2. This is 1-butene. What are we doing? We are adding hydrogen gas in presence of a catalyst, which is platinum. So this would be how your reactants and your catalyst would look like. What would happen now? Simply this double bond will turn into a single bond. And our products are going, this was 1-butene, it will turn into butane. Now this is an example of a alkane, right? So we added hydrogen into this particular double bond and it turned into a single bond. Yeah. So one hydrogen went here, one hydrogen went to this carbon. We usually don't show hydrogens on the line structure. That's why you don't see it here. But if you were to draw, let's say you wrote this as carbons. So this would be C, double bond C, then I have one other single bond, another single bond. Now let's fill in our hydrogens. This carbon has one bond, so it needs 3 more bonds, so 3 more hydrogens. This carbon already has 2 bonds, it needs 2 more, so 2 hydrogens. This carbon has 1, 2, 3 bonds, so it needs 1 more hydrogen. This carbon has 1, 2 bonds, so it needs 2 more hydrogen. So this is the condensed structure for 1-butene. This plus hydrogen gas in presence of platinum would turn into, you basically open up this double bond, it would become CH3, single bond CH2, rest everything else stays the same. So this would be butane, and this is 1-butene or butene. Okay, so what we did here is we simply got rid of this single bond and we added 1 bond to each of those, and to each those bond we added, this is hydrogen, so we added 1 hydrogen atom from this molecule. So this is addition reaction for hydrogen, which is also called hydrogenation. Next, the question is asking, write the products for each of these following reactions. So what do we have here? We have, I see 1, 2, 3, 4 carbon compound, and this is again an alkene. It has a double bond. It says to add hydrogen in presence of platinum. So you should know, it nowhere says this is a hydrogenation reaction. You should be able to recognize whenever you see a catalyst, which is a metallic catalyst, it could be platinum, nickel or palladium. Any of these catalyst and hydrogen gas being added, it means this is an example of hydrogenation reaction. What would happen? This double bond will break and it will have 1 hydrogen being added to each of these carbons. So the final answer is going to be CH3, CH2, single bond, CH2, single bond, CH3. Okay, so this bond broke and each of the carbon now has 1 extra bond and they both get 1 hydrogen each. How about this reaction? This again, when you look at this reaction, this is an example of a cycloalkene. It has a double bond. We are adding hydrogen in presence of a catalyst, which means this is hydrogenation. It's an example of addition reaction. You simply open up this double bond and it will turn into a single bond. So a final product would be this. That's it. Okay, let's move on to the next reaction, which is hydration reaction. What is hydration? Hydration is where we add water. How is water added? Water is H2O. We can write this as HOH. So you will add simply, it's an addition reaction where one of the carbons is going to get hydrogen, the other carbon is going to get OH. This OH group is called the hydroxyl group. Okay, this OH is called hydroxyl. Now, if we open up this bond, right, this is an alkene, we are adding HOH. This is done in presence of a strong acid. That strong acid can be H2SO4, it can be HCl. Okay, only idea is that you're seeing this is H+. H+ means it's an acidic solution. So now we are going to add hydrogen to 1 and OH to 1. Okay, now how do we decide which carbon out of these two gets the hydrogen and which carbon gets the OH? Up until now we were adding same atoms to both the carbons, so it really didn't matter. Now we are adding 2 different groups. One is getting a hydrogen, one is getting a hydroxyl. So how do we decide who gets the hydrogen and who gets the hydroxyl? So this is given by Markovnikov's rule. Okay, this rule, remember it like this. rich gets richer and poor gets poorer. Okay, right now only part of this rule we are going to use is that rich gets richer, which means whoever is rich already will get richer. Okay, so out of these two carbons, whoever already has more hydrogen atoms is going to get the hydrogen atom again. Okay, out of these two carbons, whichever carbon has more hydrogen atoms attached to it will get the next hydrogen as well, and the hydroxy will go to the other carbon.
Isn't there sharing at the same hydrogen?
In this they do. In this particular example, this also has two hydrogen, this also has two hydrogen. So, and either one of those can get the hydrogen and the other one would get hydroxy. It doesn't matter, but this is only two carbons. If we examples, okay, for instance like this, if we pick this example, how would we know which one should get the hydrogen, which one should get the hydroxyl? So now the rule is this answer, everything stays the same. Only thing that would happen is you make this into a single bond and they both have one extra bond, right? Now we have to add hydrogen to one, hydroxyl to one. So what is the rule? Rich gets richer. Out of these two, who has more hydrogen atoms already? This has two hydrogens already, right? So rich gets richer, it has hydrogens already, this will get the next hydrogen as well. And hydroxyl will go to the other carbon. So your final product would be this. So you could write this as CH3, CH2, CH, OH, CH3. So that is your final product that is produced from this reaction. And how did we figure this out? We figured this out by using Marconi-Koff's rule. This is a rule that tells us where does the hydrogen go, where does the hydroxyl go. Okay. Alright, another thing I want to mention here, this OH is the hydroxyl group. Whenever hydroxyl group is present on a hydrocarbon, this is a functional group. This is referred to as an alcohol. Okay, we'll talk about this later on as well, but basically when the hydrocarbon has an OH group or a hydroxyl group, that functional group is referred to as, the hydrocarbon is now called an alcohol. Okay. Alright, then the last type of addition reaction we'll talk about is polymerization. What is polymerization? Polymerization is the process of making a polymer. What is a polymer? A polymer is a very large molecule that is formed by reaction between monomers. A polymer is a large molecule that is formed by a lot of repeating units called monomers. So a bunch of monomers come together to form a polymer. For instance, let's say if I have this monomer AB, bunch of AB are going to react with each other. How? You see AB, 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 they have a double bond between them. Okay, what would happen if I remove one of these double bonds? A would have one more bond to make, B will have one more bond to make. Similarly, this molecule A will have one more extra bond to make, this B will have one more extra bond to make. So what would they do? This A and B are going to form a bond with each other. Similarly, the next monomer unit, this will and this will form a bond. So what would happen? These two will now connect with each other. So what is happening? We are basically repeating the AB, AB, AB unit again and again, and this will continue until the end. It will have an end at the end, but basically this would have multiple repeating units. So the repeating unit here is AB. AB, 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 it is continuously repeating itself. So this is now an example of a polymer. And the repeating unit here, which was AB, is called the monomer. So when multiple monomers combine together, they form a polymer, and this process is called polymerization. Why is this important? Because we use a bunch of polymers in our daily life. For instance, Teflon is an example of a polymer. Saran wrap that we use is an example of polymer. Polystyrene cups that we use is an example of a polymer. Okay, nylon clothes that we wear, the synthetic clothes, that is an example of a polymer. Okay, so plastic that is used, that is also an example of a polymer. These are all synthetic polymers that are prepared by industries for different purposes. This is also an example of addition reaction. How? Like I showed you, if we have this particular alkene, bunch of these alkenes are going to come together and get added to each other. Okay, for instance, if this is ethene, what would happen? This double bond, one of these double bonds is going to break, and this carbon will have one extra hand, this carbon will have one extra hand. Similarly, one of these double bonds is going to break, this carbon will have an extra hand, this carbon will have an extra hand, and they are going to join with each other. And we end up with something that looks like this. And there are many repeating units. So what you see in parentheses here, this is telling you this is the repeating unit, and it has many repeating units. 10, 20, 40, thousands, 500. That is usually how these polymers, the number of repeating units are present in these polymers. Okay. For instance, the pacemakers that are used, or the joints, the material that is used to fix joints, all those materials are basically examples of polymers. Okay, so that is the process of polymerization. These reactions usually occur at a very high temperature. Again, they would need a catalyst and very high pressure so that these molecules can actually react with each other and come together to form a very long polymer, a long chain of monomers. For instance, you can see right here, these are some examples of polymers that are used. This is ethene. It joins together to form polyethene. The common name for ethene is, it's also called as ethylene. So this is called polyethylene. This is the polymer that is usually present in all the plastic material that is used, especially the shopping bags. All the plastic bags that we were use for shopping, those are made from this polymer, which is polyethylene. Okay. Then you see this example, chloroethene. This is another monomer that can form PVC. PVC is used in making pipes, right? So that is also an example of polymer. Again, I don't expect you guys to memorize any of these structures or with what is the monomer, but what you should be able to see is, if I give you this polymer structure, for instance, if I give you PVC and I ask you what is the monomer unit of this, you should be able to recognize the repeating unit here. How would you recognize that? See, there's one carbon which has hydrogens, one carbon which has chlorine hydrogen. Then I have next carbon which has hydrogens, next carbon has chlorine hydrogen. Next carbon has carbon with hydrogens, then we have carbon with chlorine hydrogen. So what am I repeating every single time? I'm repeating this unit where one carbon has hydrogens and the other carbon has Cl and hydrogen. So this unit which is repeating again and again is the repeating unit. Okay, and what would be the monomer? That monomer essentially should have a double bond. So you could get rid of these bonds that the carbon has formed and make a double bond between the carbon. So your repeating unit would be this. So if you look at a polymer, you should be able to come up with the monomer. And if you look at a monomer, you should be able to come up with the polymer. Okay, simply break the double bond and start joining the atoms, the molecules together. Alright, there are a bunch of examples that you're seeing, and it's telling you where these particular polymers are used. So basically you can see most of these materials we use in our daily life are all polymers. Alright, so I think this brings us to the last topic, which is aromatic compounds. So what are aromatic compounds? Like I said, aromatic compounds consist of a ring structure, which is this. 6 carbon ring structure which has alternating double bonds and single bonds. This is called benzene. You could draw it like this, or you could draw it in this form where the double bond starts here, double bond, single bond, double bond, single bond, double bond. Anything is acceptable, okay, as long as they are alternating double and single bonds. It is called benzene, and any compound that consists of this structure is called an aromatic compound. Okay, one important thing that happens in benzene is that you see here the double bond. I could take this double bond, move it here, this double bond, move it here, this double bond, move it here, and if I do that, that was going to give me this particular compound, right? Similarly, I could take this double bond, move it here, this double bond, move it here, this double bond, move it here, and that is going to give me this particular compound, right? So this process where the double bonds rotate within the structure is called resonance. So in case of benzene, the double bonds are continuously resonating, they are continuously moving around, and that is why sometimes this structure can also be written in this form. You simply draw the ring, 6-membered ring, and then draw a circle in the middle. This is also called benzene. Why? Because here the double bonds, we are basically telling you that there are double bonds and they are basically all over the place. They keep on rotating. We don't know where exactly the double bond is located because it keeps on moving. So you could write this as a ring in the middle. Okay, so this is also called benzene. Benzene can be written in this form with double bond, single bond, double bond, single bond, double bond, single bond, or you could simply write it like this. This is also a benzene, and any compound that consists of benzene is an aromatic compound. Okay. Okay, so like I showed you, aromatic compounds, they keep on rotating like this, these double bonds, so you simply can write it in this form. Okay, it is a flat ring structure which is drawn with 3 alternating double bonds. Okay, it can be represented by a single skeletal formula using a circle in the center instead of continuously drawing these alternating double bonds. So people use this as well as a representation for benzene. Okay. All right. Now there are, how do we name these aromatic compounds? There are few names that you do have to memorize. Okay. So if this is the benzene, when it has a methyl group attached to the benzene, that is called as toluene. Okay. This is a common name, but it is also accepted by IUPAC. Okay, how would you draw this as a line structure? It would look like this. There is a benzene and it has one alkyl group which is 1 carbon. So that is called toluene. If we have an amine group attached to a benzene, that group is called, this molecule is called aniline. And when we have a OH group or a hydroxy group attached to benzene, that group is called phenol. Right? So these are the 3 names that you do have to memorize. This is called toluene, aniline, or phenol. Now we can make any other substituents onto this, and this is going to be your parent chain. You could add substituents and you would name the substituents like we always name the substituents with the number of carbon. So what you need to memorize here are some derivatives of benzene, which is toluene, aniline, and phenol. Okay. So when we write, for instance, if we were to name an aromatic compound like this, okay, the first compound, what does this have? This is a benzene and it has a chloro group, right? If I'm just naming the first compound right now. What does this consist of? When you look at this, it consists of a benzene. This is called benzene, and it has one substituent which is chloro. So what would be the name called? The name would be chlorobenzene. Okay, wherever is the group located, that would be your carbon number 1, because we always give preference to the substituent. So in this case, the substituent carbon is 1. Therefore, you could write this as 1-chlorobenzene. But since it is carbon number 1, you remember we usually don't use the 1. So therefore it will be called as chlorobenzene. If we were to name this particular structure, how would we name this? Again, you recognize this is a benzene ring. How do you recognize it? Whenever you see it is a 6-membered ring with a circle in the middle, that is benzene. Okay, and now we start numbering our substituents. I have 2 substituents. Where are they located? One is on carbon number 1, the other one is on carbon number 2. You could also name this as carbon number 1 and this is 2. That is fine, it doesn't matter. Okay, so this would be called 1,2-dichlorobenzene. Okay, now if I move this chloro to this particular position, how would we name this? Again, this is a benzene. We start numbering. One of the chloros will always be 1. Okay, your substituent should always be 1. So this is 1, this is 2, this is 3, or you could also name it the other way. This could be 1, this could be 2, this could be 3, it doesn't matter. So this would be called 1,3-dichlorobenzene. The next one is 1, 2, 3, 4, so it would be called 1,4-dichlorobenzene. Okay, so sometimes, because if we are working with bunch of benzene molecules, it becomes a little bit tricky. There's also a common name given to these compounds. Whenever a substituent is present on carbon number 1 and carbon number 2 on a benzene ring, it is called ortho-dichlorobenzene. Instead of writing numbers 1 and 2, sometimes a common name is also used, which is ortho. Ortho means on benzene we have a substituent on carbon 1 and carbon 2. Okay, if the substituent is present on 1 and 3, it is called meta. If the substituent is present on 1 and 4, it is also referred to as para. Okay, so these are just some common names that are used for instead of numbers. So if somebody tells you you have para nitrobenzene, how would you draw this? We know it's a benzene, it has a nitro substituent, and it is P. P stands for para. Para stands for 1, 4. So you would draw the benzene ring. And where is the nitro located? One is on carbon number 1. The second one is on, if this is 1, 2, 3, 4, it is 4. So this would be para nitrobenzene. Okay, so instead of giving the numbers, you could simply be given the common name, which is ortho, meta, para. Ortho O is 1, 2, meta is 1, 3, para is 1, 4. Okay, so if the question says what would be the structure for, let's say, a meta bromobenzene, how would we draw this? This is meta bromobenzene. So first thing I know is this is benzene ring. It has bromo substituents on meta positions. What are meta positions? 1 and 3 are meta positions. So you would draw a benzene ring, 6 carbon ring with a circle in the middle, and carbon number 1 will have a bromo, and carbon number 2, 3 will have a bromo. So this would be your structure for meta bromobenzene. Okay. Select the correct name for each of these compounds. So what would be the first one called? First thing we recognize, this is benzene. Where is the chloro? It only has one chloro. So if it only has one substituent, that would be your carbon number 1. So this is chlorobenzene. The right answer is B. We do not call it 1-chlorobenzene because if it's 1, we don't put the number 1. Okay. Next we have this. Perfect. So this is 1, this is 2, this is 3. This can be called as 1,3-dimethylbenzene, which is this. Okay. Another thing that we saw previously is that this structure, if a benzene has a CH3, this is also called as toluene. Okay, this has a common name of toluene. So we can also call this particular structure that we just named, if this is CH3 and this is CH3, we can also call this as, I would say this is my parent chain now. I can say this is my parent chain and I have one substituent. Okay, so if this is my parent chain, what would this be called? This can be referred to as methyl toluene as well. Okay, because your parent chain here could be referred to as toluene. Those examples. So for instance, if we are naming this particular compound, what is given to us? This right here. We have a benzene ring which has this amine group and it has a bromine right here. Okay, so how would we name this compound? We know this group is called as aniline. So any benzene ring with amine group is called aniline, where aniline carbon is carbon number 1, this is carbon number 2, this is carbon number 3. So we can call this compound as 3-bromo-aniline. Aniline is our parent chain. Okay, and the numbering always starts from wherever this was. So if I have this particular compound, if I'm naming the second compound right here, how would I name this? I see this is my parent chain. Whenever I know that whenever benzene has a OH group or a hydroxy group, it is called as phenol. So my parent chain will be called as phenol, where this group is given, always given the carbon number 1. So if this is 1, I would go this way, this is 2, this is 3, this is 4. Right? Why did I go counterclockwise? So that my substituent can get the smallest number. I did not go in this particular direction because then my substituents would get a bigger number. So now what are my substituents? I have a 2-chloro and a 4-bromo. I have a 2-chloro and 4-bromo. Which one comes first? Alphabetically, bromo comes first. So the name would be 4-bromo-2-chlorophenol. Okay. Finally, we come to this structure. What do we have? I see my parent chain is benzene with a methyl group. This is called toluene. Okay. Now we use the other substituent. So how can we start numbering? I would say this is my 1, this is 2, 3, 4, 5, 6. You could go either direction. It would give you the same substituent because here 2 has bromine, 6 also has bromine, so it really doesn't matter. You could name it clockwise or counterclockwise numbering. It would give you the same answer. Now what are my substituents? I have a 2-bromo, I have a 6-bromo, then I have a 4-chloro. Which one comes first? Alphabetically, bromo will come first. And I have 2 bromos on carbon number 2 and carbon number 6. So this will be called as 2,6 dibromo. Then I write my chloro, which is -4-chloro. And then the parent chain, which was toluene. So this would be the final name for this particular compound. Okay, so that is how you name the aromatic compounds. You should remember there is toluene, aniline, and phenol. And that's all. So now based on this chapter, we have studied 4 different types of hydrocarbons: alkane, alkene, alkyne, aromatic compounds. And we saw which one is single bonds. So this is saturated, this is double bond, triple bond, ring structure. And we also saw the type of reactions that these particular compounds give us. That is it. That is this chapter of Introduction to Organic Compounds.